Now, you've learned in previous lessons that a digital certificate is like a digital ID badge, and we use it to validate the integrity of a public key. The certificate includes valuable information. Now, I want you to understand the content of those certificate. It includes valuable information such as who owns the key, that's the subject, who issued the key, the certificate authority, and a digital signature that proves the certificate is legit. The subject could be a person, like someone who signs emails, or a server, like a website that wants to secure online transactions. With computers all over the internet needing to verify digital certificate, we need a consistent and secure way to do so. Two standards were created to make sure everyone is speaking the same technical language. The first one is the Internet Engineering Task Force, and ITU. This organization standardized the way certs are formatted by creating the X.509. This standard defines the format for public key certificates, and it is a core part of the public key infrastructure. Think of X.509 as the rule book for how a certificate should look and what information it should contain. So when someone says a certificate is X.509 compliant, they're saying it follows the trusted industry standard for formats and validation. Another standard created for cert validation is called Public Key Cryptography Standards, PKCS. This standard was created by RSA. That's the same group that created the asymmetric encryption algorithm. PKCS is not just one standard, it's a collection of standards ranging from PKCS 1 all the way down to PKCS 15. In summary, they standardize how to implement cryptographic operations like key generation, encryption, and packaging. Think of PKCS as the how-to guide for using cryptography in real applications, like generating keys, requesting certs, or bundling them together. All right, now I want to talk to you about the root of trust. You already know that every cert has a signature on it from the certificate authority, right? Because we trust the CA, we therefore trust everything they sign. Now I want you to understand that every CA starts with a root certificate. This is a self-signed certificate, meaning the CA signs its own certificate with its private key. This is the foundation of trust. If you trust the root certificate, then you also trust anything it signs. Root certs use strong encryption, usually RSA 2048 or 4096 bit key, or ECC equivalent. The subject line of the cert will often look like company root CA or something similar. Once installed in your system, that root let your computer trust anything signed by that CA. One thing to note, a root cert can be a major third-party organization like Entrust, DigiCert, or GoDaddy. The root cert can also be made by your company. The difference is major third-party companies are globally known and can be used with anyone as they come pre-installed inside major web browsers and operating systems. Privately created root certs work the same, however, they can only be used on your corporate devices because your IT department only installed the root certs on those computers. All right, now let's explore how CA are structured. You have single CA model. In this model, one CA does it all. They sign every cert directly. It's common for private networks to have their own root cert. But here's the risk. If that CA server is hacked or compromised, your entire security model crumbles. And then you have the hierarchical CA model. This is what most third-party CA use. The root CA signs intermediate CAs, and those intermediate CAs sign end-user certs. That way the root stays locked down and secure. Plus, different intermediates can issue certs for specific purpose, like one for email, another for web servers, and so on. This setup creates a chain of trust. Every cert can be traced back up to the root. This is called certificate chaining. Here's an example. Let's say a web server at www.example.org has a cert signed by DigiCert, and it's called DigiCert TLSCA1, an intermediate cert. That intermediate was signed by the DigiCert Global Root CA. So when your browser sees the site, www.example.org, it follows the trust chain up to the trusted root. Done. Now, not every cert is signed by a trusted CA. Some cert are self-signed. meaning the site or device create and sign its own certificate. They're basically saying, trust me without a CA. You'll see these on things like home routers or in IT environments where the impact of a security breach is low, like a dev or test environment. This is a cheap and easy way to use asymmetric encryption, but browsers and operating systems won't trust them by default because the root cert is not installed. You'll often see warning signs like these saying the site is not secured. That's because there's no way to verify who really issued the certificate. Bottom line, don't use self-certs on public-facing or high-value systems. Use them only when you're okay with manually approving the connection or when the trust isn't critical. All right, here's a recap. I know that was a lot. Hang in there. We learned a digital certificate links a public key to an identity. We also learned trust starts at the root, literally, with a root certificate. We learned that IRCO's CA model creates safer, scalable trust chains. We learned that self-signed certs are okay in low-risk environment or private situations, but not for major production environment. See you in the next one.